So we define probability space as a triple like this. This omega is the sample space, or it's just some set. Let's not call it sample space. And this is a collection of, this is contained, A is contained in the power set of omega, and it's also a sigma algebra. What is called a sigma algebra, which is the whole omega is there, empty set is there, it's closed under countable union, countable intersection, and complement. And P is just a function from step A to 0, 1, which is countably additive. It takes disjoint, it's additive over disjoint set, countable collection of disjoint sets. And probability of the whole set omega is 1, empty set is 0, and all that. Okay. So then we define what is called a discrete random variable. Okay. We defined a discrete random variable, x is, which is just a function from omega to real line. If omega is discrete, finite, countable, if it is finite or countably infinite, we don't need anything more, it's just any function. Otherwise, we need one more condition. It is a function from here. It's called a discrete random variable. We will define continuous random variable later. This is the definition of discrete random variable. If the set of all x in R such that set of all x in R such that x omega I mean, so this is just the range of omega is countable if it is discrete. Okay, it is a discrete random variable if the x of omega, the range of omega, which is just the range of x. The range of x is countable, and the set of all omega in omega such that x of omega equal to some x. Okay, range of omega, and let it be equal to x1, xn here like this, like xi. Okay, is in A for all n. So this set, we will denote it as just x equal to xi. The set x equal to xi, which is defined as all those omega, which maps to this xi, and that set should be in sigma algebra, so that we can talk about the probability of this. This condition is needed because we want to talk about probability of x equal to xi or x equal to some set for any subset of this. See, x is a function from omega to real line, and it takes only countably many values. Okay, and if you take among those countably many values, this x1 of xn, we take any subset, we need to talk about the probability of that set. Probability of any sets, any such set, if you take any A contained in, this is the range of x. Okay, if you take any set, then we want to talk about the probability of A of this random variable with respect to the distribution of the random variable. That will be the summation of probability of all the points in this, and probability of all the points we have to talk about, and that is this. Okay, I mean, that is the probability of this set. We need to talk about it, so we need, for that, this set should be in the sigma algebra. Probability is defined only for the subsets of, only for subsets though which are in this A. Okay, that's why we need that condition. Okay, and then we define what is called a probability mass function. Probability mass function, or just mass function. F is just a function from R to 0, 1, okay, such that f of any x equal to probability p of, I mean, x is defined on some omega, then p of x equal to x. For a discrete random variable, then we know that for a discrete, I mean, x is a discrete random variable, then for this probability mass function, f of x is always greater than or equal to 0 for all x in R. Second condition is f of x strictly greater than 0 for only countably many points, because it's countably many points. We saw these things. And third condition is, so that countably many points, we call it as x1, x2 like this. Or you can just say that x in R also, doesn't matter, because it's 0. I mean, it's 0 which is equal to summation I equal to 1 to infinity f of xi should be equal to 1. That is clear because this summation is just the p of omega, which is equal to 1. Okay. So these things are clear. Then we saw some example. I think we saw only one example, which is binomial. So then we showed that, I mean, it was a trivial, I mean, the proof was trivial. If we have any mass function, then we can define a probability, space and a random variable so that its mass function is precisely f. Okay, given any f satisfying this condition, I mean, if we have a random variable, we get a mass function by the definition. Or if you have any function which satisfying these three conditions, we call it as a mass function. Okay. So if you have any f satisfying 1, 2, 3, we call it a mass function. Okay. Call it a mass function. We don't need a random variable for that. We just call it as a mass function. Or a density function, it's called as density function in some book. Okay. Then there exists omega kp and x from omega to r such that the mass function of x is f. Okay. There is nothing in the proof. You take, if you have a, take these points, it's a mass function, so it has only countably many points where the f of x is greater than 0. You take this numbers, this set, take this as omega, define f of xi equal to, I mean, sorry, x of xi is just identity function, then that gives an example, that gives a random. Okay. This is just to make sure that our definition, so it's enough to, I mean, our definition is consistent. So it is enough to talk about, so we can forget, once we know the mass function, we can forget about the probability space, which does not play any more role unless you have many random variables and other things, unless you have that. Okay. So we can forget about that and we can talk about just the random variable, and I mean, you talk about any random variable corresponding to mass function. So one example is the binomial. I mean, the first example, well, we talked about what is called the indicator function, which is a random variable. Okay, if you have any omega script p, then the indicator function, then a is in a script a, then we can talk about indicator function of any omega equal to 1, if omega in a and equal to 0, if omega not in a. Okay. Then the mass function of this is p of, I mean, the mass function is f of 1, I mean, f of 1 equal to probability of a, f of 0. I mean, this f, the mass function takes the value only, I mean, mass function is non-zero only at points 1 and 0. At 1 it is p of a, and here it is 1 minus p. So with any probability space and fixing any set, we get what is called a Bernoulli random variable. This is what is called a Bernoulli random variable. It's like coin tossing only. It takes only two values. That's called coin tossing always. Okay. So before going to next example, let's see some properties of this. I just want to record this. Okay. You can see that 1 I of a complement is this 1 minus p of a as functions. This is a function. Okay. This is the indicator function of a complement. That will be 1 minus this. This takes the value 1. This takes the value 1 in a, and a complement it is 0. And this has to take the value 1 in a complement. But if you have this definition, it will be satisfied. Okay. Similarly, if you have a, b, two sets contained in a, then you can talk about 1 of a intersection b equal to 1a times 1b. This is, you can multiply two functions. If you have two functions, I mean, this is multiply two function mean, I mean, when the function, the range is real line or complex plane, wherever you can multiply, then you can multiply the function. If you have two functions which landing in real line or complex plane or wherever you have a multiplication, any ring or something, then you can pointwise, you can define fg of omega for any two function f of omega times g of omega. Okay. So this is just the multiplication. So if you have two sets A and B, then IA intersection B, IA times MB. This is clear because this takes the value 1 in A and the complement it is 0, is 1 in B, in the complement it is 0. So 0 times 1 is of course 0. So this will take the value 1 in A intersection B, and this will be. On the other hand, this is not true. On the other hand, 1 of A union B, this is what is called, you can take a maximum of two functions. When the function is real valued, you can take maximum, minimum. So you must be knowing maximum. I mean, it is just the maximum. If we have f and g, fg of at any point x or omega, this is equal to maximum of these two numbers. Okay, this is the maximum of these two numbers. Similarly, fg is minimum of this. Okay, minimum of these two numbers. So this is just one. So this is the symbol for taking maximum. This is symbol for minimum. Then this is just 1a maximum 1b. Okay. See, if you, this is not addition. Okay. 1a intersection. So this is also true. 1a minimum of 1b. This is also true. But minimum works. I mean, minimum multiplication goes together. 1a intersection b is 1a times 1b, and 1a minimum 1b. Okay. And 1a union b is 1a maximum b, because I mean, in the intersection, if it is, I mean, if it is a minus b, where I mean a doesn't intersect b, there it is going to be 1. Similarly, b minus a is also it's going to be 1. In the intersection, if you add, it will be 2. So because of that, you have to take the maximum of these two things. That will work. Okay. And it will be true that one a disjoint union b equal to 1a plus 1. Of course, clearly this is true. You can verify these things. I will just state it. And further, so also you can talk about A union B, which is equal to 1 of 1 minus A union B is A intersection, A complement intersection B complement complement. So 1 of A complement intersection B complement, right? Which is equal to 1 minus 1A complement 1B complement, which is equal to 1 minus 1A times 1 minus 1B. Okay. And 1 will go away, and it is just 1A plus 1B plus 1A times 1B is 1A intersection, which is precisely the, I mean, we proved something, no? The probability of A union B is probability of A, probability of this. Probability is just a, so it is similar to that. Here, here. This is disjoint union, no? I don't use this notation. If the union is disjoint, we use this symbol. No, it is a function on points. Given a set, you define indicator function. It's not a set function. What do you mean by set function? What is set function? This is not a function from set. This is, yeah, probability of something satisfies that. Yeah, it's like that. Yeah, it's like, yeah, correct. Yeah. Given any set also, you can take a 1a, which will give you a function, which will not be, I mean, this will not be a, it will be a mapping from sets to function space, not to some number, right? 1a as it is, when you fix a, it is a function from omega to real number, or the number 0 and 1. A going to 1a is a function from sets to function space. Okay, yeah. Okay, if you want to think about it. Okay. Okay. So I want to say all these things. In fact, see, there is something called symmetric difference. Do you know symmetric difference of something? A symmetric difference B. If you have two functions, A symmetric difference B equal to A minus B union B minus A, which is just this union this. Okay, this is the symmetric difference. So A intersection B complement. Yeah, same thing. Yeah, correct. Yeah. So you can prove that A You can prove it. Okay, this is, I mean, this is easy by looking at it, which is just 1a plus 1b mod 2. If it is 2, wherever in the intersection it will be 2 and it is 0. Mod 2, 2 mod 2 is 0, right? So it's clear. At A, I mean, it's A, it's 1. At B, it's 2, 1. So it will become 2 in the intersection, but we are removing that. So that is equal to this. Okay. So this will imply that if you do this, I mean, see, it is like asking what is symmetric difference of A, B, C, which is not usually defined. So you can equal to 1 of, no, no, why mod 3? There is mod 2, mod 2. That is why I'm saying associativity can be proved using it. Symmetric difference, associativity of different difference can be proved using this. Anyway, that is just about sets, not about probability. Okay. So if I mean, the indicator function of asymmetric difference B is this. Okay. If you take this will be 1a plus this mod 2, and then you evaluate that will become this, and which is also equal to this. So because of that, those two are equal. You can calculate this. So this implies symmetric difference is associated. Okay. So you can prove it this way. Commutativity, it's clear, no? Yeah, because addition is commutative, so it's commutative also. Commutative is clear, directly you can verify. For this unit, this also directly you can verify by using set. This is some simpler proof, that's all. Okay. So anyway, coming back to probability. So first we defined Bernoulli, we have seen. The second example is binomial, we have already seen. Okay, which is just so here the set is omega, I mean, I call it omega, okay, with where the f is non-zero, which is just so 1 to n, okay, and the f of I equal to n I t power I 1 minus t power n minus. Okay. So this is Bernoulli. Okay. We saw some random walk. Okay. There the omega is -1, you take +1, -1, n. I mean, we talked about this. You start from here, 0, up to n, okay, and similarly up to -n. Okay, so you toss a coin, and if head is there, you go one step further, or you come behind. Okay, so that will be like, so any if you have omega 1, omega 2 to omega n, okay, this is a point n tuple in omega. Okay, then x of this omega equal to this, omega bar equal to this, let's say. Okay, then x of omega bar is going to be summation omega I. Okay, and which is equal to k if number of +1 in omega equal to k. Okay, and then what is x? X of omega bar equal to L m if number of +1 is k and number of -1 is n minus k. So summation, so if you add those, if you, I mean, the difference is 2k minus n should be equal to m. So m should be, yeah, and k should be n plus m by 2. Okay. Okay. Right. K should be n plus m by 2, or no, m, right. Okay. So x of omega bar equal to m, I mean, the probability of probability of x equal to m equals 0 if m plus m is odd. Okay? And probability of x equal to m equal to if m is even is you have to take how many of you have to take n, you have to take choose k of them, okay, and then p power k 1 minus p power n minus k, where k equal to n plus m by 2. Okay, is okay, no? I mean, the random walk, I mean, the probability of you being at the point m, okay, but this m should be the summation of this omega I, right? Summation of this omega I. Summation of omega I is exactly how many plus 1 is in omega in the tuple. Okay. K m plus n by 2, yeah. Okay. This is number of k which are plus 1. Okay, then n minus k will be the minus 1. So it is just, if you use that, you, unless this k is, I mean, unless n plus k should be n plus m by 2, which is as an integer, it's possible only when n plus m is even. Yeah, if n is odd, m should be odd. So we got the condition. Okay. Anyway, you work it out. Someone worked it out. I don't know if it matches with the answer. Okay. So that's random walk. Then the third example. So then, I mean, I want to list out few examples of probability mass function. So to verify that it's a probability mass function, we have to verify only 3 conditions. It should take countably, I mean, it should be greater than or equal to 0, or it is greater than, strictly greater than 0 only for countably many points. Mostly it will be finite here. And the sum should be equal to 1. And here it is direct, so it will work. There is something called hypergeometric distribution. That is binomial distribution. It's called hypergeometric distribution. See, if you have n objects in a box or somewhere, okay, among that n objects, n less than n, of course, is of some type, okay, of type 1, and n minus n is of type 2. There are 2 types, type 1 and type 2. Okay, you call it type 1, type 2, maybe red balls and black balls, whatever. Okay? There's something. You have n objects, among them small n number of times, so small n number of times objects are type 1, n minus n number of objects is of type 2. Okay, then you choose k objects, okay, from this n. Okay, they are all identical objects. Okay, k objects. So the probability of getting r number of number of type 1 objects. Okay. You choose k objects from the n. This is n is the total number of objects. From that you choose k objects, k number of objects. So there are many numbers going on. You have n objects. Among that, small n is the type 1 number of objects. N minus n is the type 2 number of objects. Now you choose k objects from here. What is the probability of getting r objects, r number of objects which are of type 1? Okay. Even though it's long, the solution is easy. So the total number of, I mean, you have to list down what are all the possibilities in the sample space. Okay. So the proper, I mean, we don't write the sample space. We will just count down the number. The number of possible choices are n. You are just choosing k objects from here. So this is the number of total number of things, right? N choose k. N choose k. K is the number we are choosing. We are choosing k objects, right? Okay. Among them, you have to choose, among n, you have to choose r objects, right? Okay. So n, r, right? R objects. And then you have n minus n, and here it should be n minus r. That's all. That's all. So probability of r, p of r, or f of r. mean, R is the value. The sample space, the density function, the values are, this is the value which is 0, 1, up to, there are n, no? N is this. Okay.
So the mass function that you're defining on the random walk is the
Yeah, mass function, probability function are same. I mean, it is just the how you want to interpret. See, you have mass function is a probability of those points, single points of the random variable. You can see, I said you can forget the probability space. If you have, in the random walk, we have a probability space, which is different, which is just this as 2 power n number of points. Okay. Then we got a random variable, which is our random walk. That takes the value minus n to n, half of it, not all of it, half of it. So, and then you can take that as the new probability space for the random variable, where the mass function is defined. Okay. K minus, this should be, yeah, K minus R. You are right. Good. Yeah, it should be K minus R. Yeah, now it's correct. Yeah, it's not N minus R, it's K minus R. Yeah, N minus N, K minus R. It's correct. From N minus N, you choose K minus R. Yeah, because so many numbers are floating around, so it may be confusing. Okay, this is what is called hypergeometric distribution. So we have seen binomial, we have seen hypergeometric. Third, we will see, this is a slightly different. I mean, I'm taking examples from the Hoyle-Porte stone only. These examples are there, and this will be there in every probability book. Okay, it will be the same thing. These are all fundamental examples. Okay, so the example 4. This is an example. You can take a continuous space and then define. For example, you can take your omega to be 0, 1, and you can divide this into n intervals. And now each interval you can define some constant function, a step function, for example. You know what is a step function? You can define a step function. That will take only finitely many values. A step function will take finitely many values. So that is a discrete random variable defined on a continuous space. Or, so this is another example. You can take the omega equal to the circle, R2. This is R2. Okay. Such that x square plus, this is the unit disk, that's not equal to 1. Okay. Unit disk. Okay. And of course, I don't want to say what is script A, but you want to have all open sets or all disks. Okay. I mean, this is you have to define the sigma algebra, which will be complicated. You have to take all open, so you know what is open set. You have to take what is called open set and take the sigma algebra generated by that, and you will see that when you take measure theory course. But here I want to define problem. So it is like this. You have this whole circle. Okay. Then you have smaller circle of radius 1 by n, 2 by n, 3 by n kind of. Okay. This is of 1 by n. This is for 2 by n. This is 1 by n, 2 by n, and k by n kind of thing. Okay. This is radius of k by n. Okay. K range varies from 1 to n. Okay. Now you toss a coin or do something, or you're shooting, but shooting will not have equal probability. Okay, one will be aiming here, so it will not have equal probability. So that's not the right example. You can shoot, and I mean, landing here, it will there will be more probability to land here, okay, because that is what one will be aiming at. So if you toss a coin, assume that it has equal probability for falling into any of this circle. So if it lands in this circle, you call it call the value as k, or you win some money. Okay, k dollar or k rupees, whatever. Okay, so that is the random variable. Okay, so you can define. So if probability of any omega equal to k by n. No, what is the probability? X of omega equal to k by x of omega equal to k. Sorry, k if omega is in you call it as this is disk, no? So you call it as ball of radius 1. Okay? B of, this is just B of R equal to all those xy. Yeah, you want to use that, you can use that. Okay. I just down to R. Okay. You call this as it's just the disk of radius R. Okay. It's also called ball, so I'm using B. Okay. So if omega is in B of k plus 1 by n intersection B of K by N complement. Okay. Right. Kth one, the complement, and then it is inside the B of, yeah. Okay. It is in this. Then you, yeah, K. You want to calculate the probability. For that, you have to define the probability. The probability is this is assume that, see, I defined what is called uniform distribution. If you have n objects, if you have n numbers, the probability space contains n elements, then each element having probability 1 by n is called a uniform distribution for a finite thing. If you have n, I mean, we define something called uniform distribution. I'll just show it here. So if your omega is 1 of the n, okay, then you define probability of singleton I by I equal to 1 by n. Each point has probability 1 by n. This is a uniform distribution. Or you have an interval 0, 1, or you take any interval, then you take the length of that A is in some interval, I is contained in here, then the length of this, okay, length of I divided by whole length, which is 1. So you call that as the probability of this. Okay. Similarly, for this whole thing has area pi r squared pi. So you take, if you take any subset here, then the area of that subset divided by pi is the probability. Okay. So define P of any set A equal to area of A divided by pi. Okay. Now you want to compute the area of this. Now area of B of K plus 1 by n intersection B of K by n. So which you can just calculate pi r square, the K plus 1 square minus K square divided by n square. And this is just A plus B minus A. That will be 1, and this will be 2K plus 1 by n. You can just do the calculation. So f of K, so even though this is a bit complicated space, this is a disk and it has all the sigma algebra and other thing. The random variable, the mass function is trivial. Even though the space is continuous and sigma algebra, everything is complicated here. I mean, it's simple. The probability is defined in a simple way, but the sigma algebra, the sets can be complicated and all that. Even though, but still, this f of K is just 2K plus 1 by n square. Okay. It takes finitely many values, and so the random variable can be simple. Okay. So this is an example. So we have seen 4 examples. Fifth one is, this is called geometric distribution. There is something called geometric series. It has something to do with that. So that's why it's called geometric distribution. See, it is like you toss a coin. You toss a coin. You go on tossing the coin till you get a tail, till you get a head or something. Okay? So you have a coin which is probability of getting a head is P, and suppose you have P of H is P and P of small p. I mean, this is P but small p. Okay, and P of tail is 1 minus P. Here it is just, this is just function. 1 minus P. And you go on tossing the coin till you get a head. Okay, you may get it any time. You may get in trillionth time or anything. So it will be, the probability space should be the random variable is from, I mean, this is just HT. The probability space will be this HT. You take infinite direct product. Okay? You have to take the infinite direct product, right? Because you can, yes, yeah. It may be, you may have to do infinite. I mean, you may, the number can be anything, no? You may go on doing it. The probability space, you include all possibilities in the probability space. So it can be anything. Okay. So we don't care about the probability space. So we just want to, we are worried only about the random variable. The random variable is at the nth task you stop. Okay, so n can be anything. So that's why it's infinite. Okay, so the probability of x equal to, we don't care about, see, as I said, we don't care about the probability space. I just write the x equal to some n equal to, you want to get head in the nth task. So within the nth task, there should be n minus 1 head, right? N minus 1 tail. No, till the nth task, it should be all be tail, right? So it is just p into 1 minus p power n minus 1. Or you have n where n,
Probability of x equals n is the head on the n.
right, and everything before that, everything is tail. So this should be 1 minus p power n minus 1, 1 minus p power n minus 1. But I want to start from n equal to 0. Okay, n equal to, I mean, just for our, or otherwise I will miss something in when you do the computation. Okay, it's better to have n equal to 0 to 1. I mean, 0 is first task you get a, okay. So 1 minus p, there are n of them. N could be 0. Okay, so this is the probability. That's all. The function is simple. P into 1 minus p power n. Okay, so okay. So let us see what is okay. So you can calculate this set, probability of x less than or equal to n. Okay, which is just probability of x equal to k, x equal to 1, x equal to 2, x equal to 3. So this is the summation of k equal to 1 to n. 0 to 1. Sorry. Is it n minus 1? No. No, no, let's call it n. Starting from 0. So it is, call it n. Okay. Because I want to get something, I don't want to get confused again, use the n minus 1 there. Okay. So probability of x equal to k. Okay. Probability of x less than or equal to n is summation of all these things, right? So which is just p times summation 1 minus p power k, k equal to 0 to n. So which is just p into, you remember the formula, 1 minus p equal to q. Okay. I call 1 minus p equal to q. So this is just q power n plus 1, right? N plus 1 by 1 minus q. N plus 1 or n? It's n, right? N. Okay. No, it's up to starting from 0. Okay, so it should be okay. Okay. That's not the point. The idea is what matters. Okay. So it is this. Now 1 minus q is p. So it is just 1 minus q by n. Super. Okay. Now notice the following. Now the probability of x greater than n, okay, which is equal to 1 minus probability of x less than or equal to n, right? Okay, it is just the complement of this. Okay. Probability of a is 1 minus probability of a complement. Okay. So this. Now probability of x less than or equal to that we have calculated, which is just 1 minus q power n. So which is just q power n. Right? Is it okay? So I mean, we have calculated the probability of x equal to n. You can take that as a definition if you want. Okay? I just use that example to motivate. I mean, it is like the experiment of getting a tail. The experiment can be anything. Okay, you may be shooting and maybe you have the probability of p 1 minus p, and it doesn't change. I mean, it's like doing the experiment. The experiment is independent. Okay, when you do the nth time, I mean, a shooter may get experience and shoot better in the nth time, but that's not what we think about. You do an experiment so that it has no effect. The nth one does not have effect on the okay. Change it to n plus 1. That's what I thought. There are n plus 1. Okay. Yeah. That doesn't matter for what I'm going to talk. Okay. So the probability of x greater than, no, I don't want to go on correcting. He said it's n plus 1. So I just changed here. If this is n plus 1, that is also n plus 1. Okay. I don't want to pull the board and tell you. Okay. Change it. Okay. Okay. Probability of x greater than n is q n plus 1. Okay, this is not, that's not the point. It is some q power something. Okay. Now you want to compute this probability of x greater than m plus n. Okay. Given that probability of x is greater than n. Okay. You know that x is greater than n. Okay. Till n, you have got only tails. Okay. You haven't done. So what is the probability of x greater than m plus n? Okay. So this is equal to probability of x, this set. You take this set, x greater than, I should have put the set notation here. I mean, or you can write it like that. You can understand. Okay. This intersection probability of x m plus n, intersection of x greater than n, okay, divided by probability of x greater than what is in down n. Okay. This is the definition of conditional probability. I'm just using the conditional probability, and that is equal to, this is x is greater than m plus n, intersection x is greater than n. Okay. This is greater than m plus n, it is certainly x is greater than m. So this set is contained here. Okay, not the other way. I mean, the bigger the number, the bigger the number that is contained in the containment is, this set is smaller. Bigger the number, set is smaller. Okay, so this set is contained here. So this is just probability of x greater than n. Okay, and this x greater than m plus n, the smaller set. Sorry, m plus n. Sorry, I mean the intersection will be the smaller set. Okay, smaller set. So this is just probability of x greater than n, which is just q of, I mean, you have one, doesn't matter, it will, it's just q of it. So that this probability does not depend on m. Depend on n. So given that something has happened till n, does not have any influence on what is going to happen at m. Okay. So the probability remains same. This is the same probability, right? This is equal to probability of x greater than m. X greater than m. The same as that. So so this is what we got. Probability of x greater than m plus n given x greater than n is equal to probability of x greater than m. It is like starting n. Okay, starting from n. This probability, this is called forgetfulness property or the memoryless property of this random variable. Okay, this random variable does not remember what happened at the nth stage when this one.
Yeah, when you do it, you get a plus one. M plus n plus 1.
M plus n plus n plus 1.
Yeah, so then you get
What is plus 1?
m. But that is greater or equal to m.
Greater than, that's no greater than or equal to. Where is greater than or? Which inequality?
The q for n is equal to probability of x. That is equality is not true.
This equality is not true.
That is greater than or equal to x.
No. Probability of x less than or equal to n is 1 minus this. Probability of x greater than m is cube here.
That's a plus 1.
Okay, plus 1.
So it's a greater than equal to x.
There should be some mistake somewhere. I don't know. Yeah.
I mean, that is same as greater than equal to x. Greater than or equal to x.
Okay, you think about it and write it properly. It will work. Okay, the idea is, it. I mean, it's.
No, that doesn't affect it. Yeah, it is equal. It is greater than equal. That's correct. The logic is correct.
Now, what is that?
No.
No, it's not affected. I think it should be exactly equal to Q power M.
Yeah, it is Q power M, but that is probability of X greater than equal to M. The logic is still correct. It hasn't affected it.
Q power M.
It still hasn't affected it. So the greater than comes from the initial.
Okay. Okay, this is okay. Okay, good. Okay. It is Q greater than or equal to M. Yeah, that is equal to that. Yeah. I don't know if I get instead of Q n plus 1, if I get Q power n, it will be nice. For that, I have to do some change. You can think about it. Okay. So this is what is called geometric distribution. The next one we want to look at is what is called a Poisson distribution, which is another very important distribution. No, there is something called more generalized geometric distribution. There is something called negative binomial distribution. So we will discuss that and then go to Poisson distribution. Okay, how much time I have? Okay, here I will not give any example. I mean, this is like, but we will have, I mean, some alpha strictly. I mean, this is example 6 or something. You have alpha greater than 0, some number, real number. If it is integer, it is like the geometric thing with see, you stop when you get r number of tails or something, r number of heads or something. Okay, I mean the geometric is till you get one head. Okay, so you can till you get r number of head, you do the experiment. Okay, it's like that. We will see how we get that. Before that, let me write the probability mass function and show that it's a probability mass function. Because see, there are you have to show. I mean, I forgot to say that. Here, this is the probability mass function you have to show. In all the other example, it's trivial, but here you have to show that this is a probability mass function, which is clear because summation of f of n, if you just sum it, that will be, you get here, if you, this is just p here, and if you just sum here, it will be 1 minus 1 by q, right, which is equal to 1. You have to verify this. You have to verify that this is a probability mass function. Okay? And it's clearly takes only countable, I mean, it's positive, strictly positive only in countable number of points, and the sum should be equal to 1. I mean, this is the basic thing you have to verify. The sum should be equal to 1. Okay. So that we verify for this, which is also easy. This is just the Taylor expansion. And you define probability or f of r. Let me write it, and then is like p power alpha 1 minus p power r will be, here comes something, minus alpha. I'm just defining a function. I'm just defining a distribution. Okay, and I will tell you that when alpha is an integer, this is like doing the, I mean, it's a generalization of geometric distribution. Doing, yeah, minus alpha. You can define this NCR for any number. Huh? If you have any alpha, any beta times r, which is just beta into beta minus 1 and beta minus 2, you just compute it till beta minus r plus 1, okay, and divided by r factorial. R is a number. R is a natural number. R is a natural number. This in Taylor expansion and other things you will do that. There is a negative expansion. Okay, so you need this. This is just the definition. This can be any number. Okay, we'll come to that. So I think it is R. Okay, let's see. Okay. I think I remember correctly. Minus 1 power r into p power alpha 1 minus p power r. Okay. Okay. R is equal to 0, 1, 2, 1 like this. Okay. So the claim is F is a mass function, probability mass function. Clearly, it is, and it's equal to or equal to this, it's equal to 0 otherwise. Okay. Okay, otherwise. This is otherwise. OW is otherwise. Okay. Okay. In all the other points, I mean, it takes only, I mean, it's positive only at countably many points, and it's clearly, you have to verify it's positive. So it is positive because there are R number of terms, right? Minus alpha R equal to minus alpha minus 1 up to minus alpha minus R plus 1. So there are R number of terms by R factorial. So this is equal to, you can go from here, minus 1 power R into alpha plus R, alpha plus R minus 1, and up to, I mean, alpha plus R minus 2 up to, the first one is alpha minus 1, right? So alpha minus R plus 1, R minus 1, right? No, alpha plus R minus R minus 1, right? Which will be alpha minus 1, alpha R plus 1, R plus 1. So which is same as minus 1 power R, alpha plus R minus 1. I'm just right. I could have defined it that way. For some reason, it is defined like this. Okay. R. This is same as this. This is a positive number, and here minus 1 here. So this will be positive number. So f of R is basically this alpha plus R minus 1 R into P power alpha 1 minus P power R. Okay. Which is positive. Okay. Yeah, this is the choose. Yeah, that's the definition. You will get it here. Right. Yeah. It is just R number of terms. You go on subtracting one. See, it comes here. You know Taylor expansion. You know Taylor expansion. To take the derivative at 0 and then, I mean, nth derivative, and then you write that formula. So 1 T power alpha will be summation. It's very similar to binomial. It is just minus alpha R T power R, right? 0 to infinity. Okay. Now you take T equal to 1 minus P. Okay. That will give you P power alpha equal to P power minus alpha equal to summation R equal to 0 to infinity alpha R, and there is a minus 1 power R. Minus 1 power R P power R. Okay. P power R. So this implies f of R 0 to infinity equal to 1. Okay. So this is a probability mass function. This is Taylor formula. Okay. Taylor series expansion. You consider Taylor series expansion of this function. Substitute T equal to 1 minus P. Okay, then you get this, and from that it follows that this is a probability mass function. Okay, so we have f of R equal to, I mean, this is just to verify using this Taylor expansion to prove it. Okay. This is a discrete function. Yeah. I mean, it is just the, you have the Taylor expansion, use it, you can use it for anything. Okay. P is not discrete. This function is not discrete. Minus alpha. This is the formula for that. Yeah. Yeah. Minus alpha I started with. Yeah, correct.
It starts from minus alpha.
Right? Yeah. Yes, correct.
It starts from minus alpha.
Minus alpha minus 1, right? Yeah. Right. Now, what do you want to start with?
Minus alpha. The first thing is
The first thing should be minus alpha. You are right. Yeah. Sorry. Yeah, minus alpha. Yeah, first thing should be minus alpha. Yeah, you are right. First thing should be minus alpha. Yeah, that is the definition. And here also that is the definition. That's why you get alpha plus r minus 1 or p power alpha 1 minus p power r. See, here it's like I still have one problem. There also I had, here also I had. See, the point is you toss coins, okay, successively. You stop when you get r heads. Okay, that means you stop at the I mean alpha is a number. So suppose alpha is in n. Suppose this function, the probability density function is defined for any alpha. That's a different thing. You get a random variable. That's different. Okay, in the real life example, I mean in a motivating example, you take alpha equal to n. Then in the alpha plus r minus 1, you should have got r heads. You are assuming that I'm getting a minus 1 problem. No, the thing is, you toss it alpha times, you toss it alpha plus r times, okay? And you should have got, you toss it alpha plus r times. Let alpha plus r equal to y. Call alpha plus r equal to y. Okay, then this becomes f of r equal to y minus 1 r, okay, p of p of alpha is y minus r, right? Y minus r, 1 minus p power r. Okay, y is a number. Okay, y is number. Okay? N. So if you toss a coin, go on tossing a coin, the probability of the first y times, first y tosses, you should get r minus 1 here. I mean, this is the definition I copied from the book, but this is not, it's not written in the book. So it's not consistent with what I'm trying to give you as an example. I'm supposed to get r minus 1 here, then it will work. I mean, if you have r minus 1, for example, if you have r plus 1, then here it should be r plus 1. That is my problem. Okay. I mean, I can change it, but that is what, so I will go through it again and come back to you. But the idea is this. The idea is if you toss a coin and you stop when you get r heads. Okay. So you stop at the yth point. So the y minus, till y minus 1, you should have got r minus 1 heads. Okay. It should be r minus 1 here. Then this is the probability of the other probability of for getting it p power y minus r and 1 minus p power r. Okay. Anyway, you have to, when you want study our proof mathematics through pure probability, I mean, when you study probability through pure mathematics, this is what you should remember. This is the definition of negative binomial distribution. Negative binomial distribution. Okay. And the motivation is generalization of the geometric distribution, where you do tosses and you stop when you get r number of heads. Okay. And as I said, here it should be r minus 1. Okay. Alpha plus r minus, what are you saying? Alpha minus here, first line here. Above alpha plus, above that alpha plus Yeah. Here alpha plus r minus r plus 1.
What the last term?
Last term, okay. This is r. Yeah, correct. No. Yeah, because from the earlier he corrected the mistake, no. So I didn't correct it again. Yeah. Then it will become r minus 1. This will be r minus 1. It's okay. Good. Yeah. That is what I'm wondering. Where is that minus 1 coming? Good. Thank you. Yeah, this should be r minus 1. Okay. Yeah. Anyway, you should work it out. Okay. So, yeah, that is how we get r minus. So now the example is clear. Okay, this is the geometric distribution where you toss coin and still when you get, yeah. So now it's clear. You stop at the white toss. So till y minus 1, you should have got r minus 1 head. So that is the probability for this.
Items in R boxes.
Yeah, something like that. Okay. Okay. So this is what is called negative binomial distribution. So the most another very important distribution is what is called Poisson distribution, which has its application in physics everywhere. It's there everywhere. Okay. And in real life, they say getting a telephone call at a particular interval or something, but it's much more important than that. So I will not give an example. I will just tell you the probability distribution. Okay. So 7th example, lambda is a number greater than 0. Okay. You know the exponential e power minus lambda. Then probability of f of n equal to n is equal to 0, 1, 2 here. Okay. Then f of n equal to e power minus lambda, or you can write it as lambda power n by n factorial into e power minus lambda. Okay. And clearly this is greater than 0 because lambda is greater than 0. This is greater than 0. And it's strictly positive only in countable number of points. And summation f of n equal to n equal to 0 to infinity e power minus lambda into summation lambda power n by n factorial. And this is the definition of e power minus lambda. E power lambda. So e power minus lambda and e power lambda. Okay. So this is what is called Poisson distribution. Okay. If I have more examples to say, I will get that later. Okay.
So there's this famous example that, like, on a road, like, number of cars passing through the coast.
The traffic light, something. Yeah.
But when I read it, I did not understand how it is.
Yeah, I cannot think about it now. We will think about it later. Okay. So I will look at that, and these things. I'm not a probabilist or combinatorics or anything. My subject is different. I'm just. I think I'm able to do some reasonable. I use probability, but I don't work at probability. These things I have seen nearly 20, 30 years back. Okay, so I'm just doing it again. I'm doing it after some 30 years. You must be more comfortable with this road example and all those things. Okay? But you will still think about it. Okay, I'm just experimenting it. So. Okay. As I said, this course is mostly, we want to concentrate on the mathematical point of view. Even though we motivate through all these examples, okay, our idea is to use distribution and all those things, how the mathematical framework of this probability. Okay. So next definition is, if you have a definition or something, if you have a function, any function, okay, not continuous or anything. Usually, any function can be anything, no? Even continuous functions can be very weird. You know that? Okay? Do you know that? Continuous functions can be. There are continuous functions which are not differentiable at any point. There are functions like that. In fact, they are much more than differentiable functions. They are much more than that. That's called, you will study it. That's called second category or something. There are It's like irrational numbers. There are more irrational numbers in the sense that they are uncountable, uncountable irrational numbers are countable, right? So rational numbers are small, even though it's infinite, it's small. Like that, differentiable, a function differentiable at one point, at any point, at only one point, at least one point. Those functions are very small when compared to nowhere differentiable functions. Yeah? Say it again. Meager set, you are right. Okay, so you have studied some topology. So till, I mean, are you learning it? I mean, you will learn it in the analysis 3, I think. Okay? It's a very meager set. It's not, meager means it's very small. It's no, it's not comparable with that. That's very big. Even though they are all infinite set. So you have any function, and x is any random variable defined on some probability space. It doesn't matter. X is a random variable on some probability space. For the time being, let us have the probability. Okay, we have a probability space. Then, and x is a discrete random variable. We always, for the time being, work with discrete random variable. Otherwise, I need to change the definition. Okay, otherwise I cannot take any function. Okay, now I can take any function. Okay, x is a discrete random variable on this. Then f of x is also, it's very clear, also a discrete random variable. You have a random variable, you compose. X is a function, f is a function, so f of x you can compose. This is just composition. F of x means composition, or or you can use this. Okay, this is the same. You say f of x is this. I write f of x means one random variable gives rise to another random variable. It's like acting f of this. Okay? That's why I write f of x means f composed with x as function, but I don't write like that. I write f of x because it is just the function of that random variable. Okay, that's what I want to mean. So that's why I use f of x. So f of x is this. It's also a random variable, and proof is clear. Of course, x takes values, x of omega, x takes values from x1, x2 up to this. Definition is, this is f of x, function of a random variable. Sorry, it's a proposition, okay? Proposition. The definition is this, function of a random variable, okay? The definition is f of x is a function. The definition is included. Okay, you should be mature. I have a function, I have a random variable, compose it and call that as f of x. That is the definition. Okay. And that is also a random variable, is what a proposition. Okay. I change it to proposition. That is a proposition. Okay. To verify that's also a random variable. Yeah, we have to verify one point. It's in the sigma algebra. Okay. So x of omega is, let x of the range is this. This is a discrete random variable, so range is this. Okay. Then so f of x of omega is just f of this set, right? X1 of no, f can be real to real. F can be any function, no? See, the problem point is you may have a random variable x, you may have a random variable y. You may have consider f of x and f of y, for example. Okay. Square is it is actually a function on this only. When you compose, you are only composing on these points. That is a point. Okay, but f can be anything. Okay, so f of x of omega is this equal to this, right? F of x1 like this. So the values are discrete. So the range is discrete, and we have to consider this omega such that f of x of omega equal to some f of xi. Okay, it is inverse image of, it is all those omega such that xi is in f inverse, xi equal to some y. You know this notation. Inverse of, it's just the inverse image of some set. Okay, this is a notation. This is not, f is not invertible or something. Okay, it is just the inverse image of a set. all those points which gets mapped to this. Okay, that is what. So f inverse of this. So xi is here. Okay, omega equal to, sorry, omega such that x of omega is in f inverse of singleton y. Earlier I wanted to write something, so this is the right. F of x omega equal to some y. Okay, you have to verify it's a discrete random variable. You have to verify that this set is in the sigma algebra, right? Definition of a discrete random variable. I mean, the range should be discrete. The another one is, for if you take a point in the range, then all the points which gets mapped to that point, okay, all the points in omega, the sample space which gets mapped to that point should be measurable. It should be in the sigma algebra. Okay, so that is what I am verifying. You take a point y in real line, then all the omega such that f of x of omega equal to y, which is same as some x of omega equal to f of y, right? So which just means that x of omega is in this inverse image. Okay, and that is equal to it is just the disjoint union. I mean, it's just union. Okay, union or disjoint union doesn't matter. Union of all. Huh? Where is I? There is no, this is just, I didn't erase properly. This is just y. I wrote xi or something, I erased it, and it is just all those omega such that I mean it is this union of all those x in, which is just a finite set. Okay, f inverse of, or a discrete set. I mean, it can be discrete, it can be countable set. Okay, I mean, this set is countable, so it is just the union is countable union. That's what I want to say. Such that all those omega in omega, such that x of omega equal to x in a single point. It's okay. X is in this. This is countable. Okay. Okay. And this set is in script A by definition of the random variable. Okay. Countable union of sets. Script A is closed under countable union, so this is in script. Okay. And you have to verify this. Otherwise, probability is not defined. So if you take any function, then you can compose that with the random variable. We will talk about function of the random variable. Okay. I think I will stop. We'll recall this and then